So it start recording in OBS. So OBS start to record. So I'm gonna have to send it from the OBS studio. All right. So we're
No,
gonna share.
so also,
Yeah.
yeah, before class start.
Yeah.
So also, I still now see some of my grades I mean, from year two,
From
semester one, you know.
we're supposed to fix up those. Um, somebody made a request yesterday as well too. So we don't have enough time tomorrow because I have one more exam to write and it's very tedious. I have to be writing six exams and some persons write only one and it giving them a lot of trouble. And I have six, so as soon as I get some chance tomorrow, then I will see what I can do to put on as
Yeah,
much
man,
grade.
because a
Cause
year two that I'm in a year three,
right,
second semester,
not
get
not
the year.
not that the grades don't go into the to triple CJ. It's just that it's
Mm-hmm.
not an ISM. ISM is different from triple CJ.
Yeah, man,
ISM,
me know, but me
right?
just no know. I'm a graduate, I have no I'm a final GPA or nothing.
Oh, okay. All right, so I'm gonna try to see if I can find a way tomorrow to put it on. All right, to put it
All
put,
right.
only for my class or for other classes.
Uh, three grades alone was for year two, semester one. I think
Okay.
all of semester two for year two gone in.
Oh, so
Just
is it
semester one.
is it my course or other courses?
I know, man. About other persons as well. Man, I gotta check. Hold on, I'm gonna look.
Uh-huh. Just remind me before the class finish. You know, because like we're recording now. Um, no, we don't start recording. So you can look fast and tell me. We don't start recording it. Huh?
Your one is there. So I have electronic circuits and devices.
Oh, that one there.
Introduction to management and communication too. And I have the other rest of them this semester one.
Okay. So my one is okay.
Yeah, your one is there.
Oh, oh, Miss Bachelor was saying to me, say some persons still don't put on in the grade. So she not seen in the grade for some persons who didn't. So I'm gonna have to check Mr. Manuel them and check everybody who taught the class and taught Mr.
Yeah,
Gustav them and
because
everybody else to find out what is going on.
but we
All
get
right, so put
everything
on.
for semester two though for year two. Everything
Okay.
is but
All right.
just on the
I'm
free
gonna ask
semester.
them. So what to do? Email me the ones that you're not seeing so that I can go to the relevant persons.
All right, I'm going to do that too.
Right. Utah, you can do the same thing too. If you're not seeing a certain thing, just email me with what you're not seeing.
What
So that
I'm
I
not
can.
seeing, and
Just email me. Yeah,
no, what
email me. Eh?
no, I'm seeing everything for the associate, but you made that change. You made that change for some, but when it changed. But guess what? When I receive the original copy from the school, it's reflect on it. It's just not reflecting on the ISIM still,
Okay.
but everything is reflecting on the original um
Remember the time when when something changed on the icing, but it never it changed on the grade sheet, but it never changed on the icing, something like that.
yeah.
I
What
think it's
about
the same situation.
the original transcript that I got from the school
Eh.
reflecting the right thing, just the ISIM still. So, but me not really too have answer the ISIM
Okay.
from the original.
From the original thing there, that good. All right.
All right, y'all set now, sir.
All right. Okay. So we're recording. So we're gonna share now. And last time we were dealing with oscillators, and we have various type of oscillators. And we know that oscillator is one of the art of the course and one of the art of most electronic devices. All right. We have some of the devices we can use oscillators in. What are some of the devices oscillator?
Radio,
Mhm.
TV,
Yeah.
the RCM multimeter.
Mhm.
You have to have measuring instruments.
Mhm.
Anything that anything here, oscillator is used oscillator is used in anything that would I say we have capacitor, inductor.
Mm-hmm. All right.
Cir-
Like computers.
computers.
All right. Where mainly would you find oscillator in terms of using inductor and capacitor?
Yeah, mainly.
Mhm.
Like us, if you're using like FM or AM, them thing them,
All
and
right, all right, all right. And if you're using a crystal, where would you like to find a crystal
com-
oscillator,
computer circuit board.
computer circuit board, or an electronic circuit board like those?
Yeah.
All right. And we have other type of oscillators. What are some other type of oscillators?
Apart from the they call pit, the arm
Culprit
culprit
and the
and
clap
the Armstrong and them so
and the
no,
clap,
no,
and you have the
crap.
Hartley, and you have the
Uh,
RC, right? And you have the Wayne Bridge, right? So you have different type of oscillators. So we're gonna play some videos after I show something right here. So we're gonna discuss this simple oscillator right here. So this simple one. So this simple oscillator, right? So this is 200 millihenry, and this is 10 picofarad. Um, See if you can calculate this frequency. The frequency for this is just an inductor and a
capacitor.
capacitor.
Pick up from that
So
one. Pick up what? 9,
no, pick a 12, 12.
12, yeah, 12,
Mm-hmm.
12, 12. 10 to the
So
negative.
right, and oh, by the way, Utah and
Yes,
Carl
sir.
and Courtney,
Yes, sir. Yes, sir.
you guys must have a scientific calculator. You're a scientist, you know, so you
Oh,
must
me,
have a scientific engineering calculator. Cause you have engineering, you're engineering technologist. So you must
I'm,
have an engineering scientific calculator.
just take a picture of my scientific calculator, just put in our calculus soup with Mr. Gustav. I just take it, put in there.
Oh,
Be
okay,
sure it's
okay.
the calculator.
Right, exactly. So now you can use it up now because when you go to the exam now, you're not got no time to write down anything on the paper. So you can put in this straight and put in this straight as long as you know the equation. And what is the equation again?
Equation,
For a LC, for a LC oscillator. Cause this is a simple LC oscillator.
is
And all
that
this
will be
and how do we get this to oscillate? Let me just stop it a little bit.
huh?
How do
When
we
time,
how do we get this to oscillate?
when you turn on the switch now,
Mm-hmm.
there's a voltage go to the inductor. The inductor charge up and you
Sure.
have a
Hold on,
bias.
hold on, hold on. Sure is the inductor.
No man, there's a voltage go to the capacitor. The capacitor charge up, you know, when the capacitor charge up
Uh-huh.
and it reach a full when it reach a certain amount, it
Uh-huh.
discharge.
All
So
right.
what the inductor now, the inductor receive that the current there, and
Uh-huh.
in called in inductance like a magnetic field. It starts to in a magnet in a inductive magnetic field. Then it
Uh-huh.
collapse again and charge back the capacitor.
All right. So Courtney, you understand that? You understand what you start saying? All right.
How the oscillation take place?
All right. Let me just take
Yes,
a,
sir.
a little bit. I'm gonna stop. Let me just stop this a little bit. I'm gonna take off these so that when Utah is explaining, you get a better idea. Whatever Utah is saying, that is how it go. But I want to take off these so that I set it better so that when Utah is explaining, you get a better idea of what he's saying. So let me just rearrange it. Capacitor, and we know what is that, what's the capacitor again?
A capacitor is a energy is an energy storage device. What you discharge and charge and user. Because the electric plate
Mm-hmm.
when you
Yeah.
reach when you reach a certain amount of voltage, it
Mm-hmm.
discharge. And when time reach,
Mm-hmm.
and so when time they like a polarity, it's come like
Mm-hmm.
a you don't come like a paint something. The two put different polarity,
Yeah.
and then when you build up, it
Mm-hmm.
just go, and then the polarity go back. So it's something you have a polarity thing.
Okay. Okay. All right. So right now, this right here, so um, explain this now to Courtney, because Courtney never understand it fully.
Alright. In this
Mhm.
circuit, when there's a 12 volt applied to it. When there's a switch, when the switch is closed, the capacitor charge up to,
Mhm. Mhm.
and after I reach a certain amount of charge, it
Mhm.
discharge. So the discharge current discharge to the inductor. The inductor,
Mhm.
which is a coil, a current passing through a coil create a magnetic field. So
Mhm.
the magnetic field it go expand, then it
Mhm.
collapse. When it's collapsing back, it create back
Mhm.
a current back in the wire, send it back to the capacitor.
Mhm. And what happened after that?
And the capacitor charge again, and it just continue, but it does stop because there's friction in the wire because it will stop over time when time circuit, when time switch open.
Okay, all right. You hear that, Courtney?
Yes, sir.
All right. So we're gonna use two things. We're gonna use a frequency counter, and we're gonna use an oscillator to check the frequency and the voltage and so forth. All right. So and we're gonna use the oscilloscope, but we're gonna use the frequency counter first. This is the frequency counter right here. So we're gonna check the frequency. All right. So we're gonna check so we're gonna put it right here. We're gonna call this output of the circuit. 'Cause I want to see what's going on with the one entire circuit. Right. We also can put an oscilloscope here, right? And same place where this is, we can put the oscilloscope because it's the same output. This.
Hmm.
All right. So we're gonna turn it on now, and then the capacitor gonna charge up, right? But if I run the circuit in simulator and I look at the frequency counter, we won't get anything because nothing don't start oscillated.
Hmm.
Here it start to oscillate now, just like what you say. If I close the switch, the capacitor will charge up. When it charge up and it reaches to the 12 volt, it will discharge through the inductor. The inductor will build up a magnetic field, and the magnetic field will have, will possess energy in it. It creates energy in the magnetic field. This magnetic field, it will collapse and try to charge back the capacitor because the capacitor is connected to it, right? So in a nutshell, when the capacitor charge up, because the coil is like a piece of wire, it's like you're shorting out by the capacitor, but it's a coil. But in doing that, the energy and energy will store in the magnetic field when the capacitor is discharging through the coil. This coil now will try to because there's no sustained energy in it. It will try to collapse because there's not gonna be any more energy, any external energy. This is the external energy. The battery is the external energy, and because there's no external energy, then the energy and the magnetic field in the inductor will collapse, and when it collapses, it will send a back EMF, and that back EMF voltage will try to charge up at the capacitor. The capacitor charge up, and it will send back the charge to the inductor, and the inductor send it back to the capacitor. It's a back. As long as the switch is going to be open, it will oscillate, or it will give out a sine wave until the sine wave eventually die off. And let me show you how the sine wave is supposed to look when it's gonna be eventually die off, or when it's supposed to die off, or it's supposed to look. Right? And they call that wave a damper wave. Alright, see it right here. It's a better one right here. I see another one right here. Right. So this is a damper wave right here. So it will oscillate until it does finally does die out. Alright. Alright, hold on. Alright, see it right here. I see another one here again. right? And they are showing you an LC. So this is the wave we do like this, back and forth, 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 until it is eventually die off, right? So they call it a damp wave or a damper wave, right? And here's an LC again, and this would be the out or the output. So see, this is another damper wave again, right? So that's how the wave supposed to look. So we're gonna turn it on now, and we're gonna see what will happen. So we're gonna charge the capacitor, and we're gonna open back the switch. Realize as it starts to a frequency,
Mhm.
because a frequency is taking place right now between the inductor and the capacitor. It is sending, and the capacitor sending energy to the inductor. The inductor sending back energy to the capacitor. Capacitor send it back to the inductor, and the cycle continue like that. As long as you talk about cycle, that's something continue going back and forth. Is an oscillator. So this is a simple LC oscillator. And the simplest oscillator or the LC oscillator is known as an Armstrong oscillator. Right? Anywhere tell you see there's one coil and one capacitor, that's an Armstrong oscillator. Right? Especially if they put an energy source there. No, nobody not gonna sit down and open and close a switch, open and close a switch. So they have to use a different type of switch that can open and close by itself automatically. What kind of switch you think we can use?
Okay, that's a transistor.
Transistor. And that's why you did the switching circuit for one of the lab, so that you can understand that the capacitor can act as a switch. So you can set it up in such a way that this back and forth movement can cause the transistor to turn on and turn off. Right? So you configure it in such a way that when the wave increase and decrease to zero, the capacitor turn on, turn off, and then it turn back on, turn off, turn on, turn off, turn on, turn off, turn on. Right? According to the oscillation. And it's the frequency of the oscillation, how much time it turn on and turn off, cause the transistor to turn on and turn off. Alright? So there's also an equation that we can use to find out the frequency of what is going on right here. The frequency of how much, in other words, how much time it turn on and turn off, how much cycle it have to turn on and turn off. And that equation is F is equal to 1 over 2 pi times the square root of L times C. So it is 1 over 2 pi the square root of L times C. And let me see if I can find it and show you. LC frequency, LC. It's right here. And even if it's in series or parallel, so let me just go for this one. Even if it's in series or parallel, it is still the frequency you're gonna use. So let me just go for this now. A PowerPoint. And whether the circuit is connected as a series circuit or a parallel circuit, use the same equation. This is a series circuit right here, this is a parallel circuit, but the equation is the same thing. The frequency, which is F, is equal to 1 over 2 pi times the square root of L times C. And this is the L and this is the C. As long as you know the L and the C, then you can find the frequency. Right? So write down this equation. I know that you are supposed to have it from last week. I don't know if Carrington, if Courtney have it. Courtney, if you didn't have it, write it down. So if you are given a parallel circuit, a parallel LC circuit or a series LC circuit, this is the equation that you're gonna use to find the frequency. It no matter if it doesn't matter if it is a series circuit or a parallel circuit. All right. So you're gonna look at this capacitor value and this inductor value, and you're gonna change those values into the basic value or the basic unit, and then you use the basic units to calculate the frequency. So this one right here, so is 10 divided by 1 with 12 zeros. This one is 200 divided by 1000, the milli, you divide by 1000, which is what this is saying. This is saying 200 multiplied by 10, 200 multiplied by 10 to the minus 3. This is 10 multiplied by 10 to the minus 12. So convert this and then you convert this. If you have a calculator, just type in 10 exponential negative 12, and you can type in 200 exponential negative 3, and it will give you the basic. If you don't want to go through that route, just say 10 divided by 1 with 12 zeros
No,
times.
and just I'll put the 10 just and say it's 10 times exponential,
Mm-hmm.
and then it's a negative 12,
Mm-hmm.
negative 12, a negative 12. So when
All
do that
right.
now? When we do that
Uh,
now, we get 1 to the negative 11, 1 to the
all
10 to
right.
the negative
So press inverse engineer until we get a second function engineer.
inverse.
Now inverse our second function. If you press the engineering key, did it increase or decrease? If you just press
And
the
for the
engineering key by itself.
inverse key, me look for. Oh, engineer key. Just press in. I mean, just you press the inverse key alone. Engineer key,
Right,
I just
right, and if you don't see inverse, our
no.
second function is shift. You're going to see.
No, me see engineering. Somebody just press that key alone.
Yeah, press it and look at the number. And tell me if the negative number increase or decrease.
Increase back, increase to the, you go back,
All
increase.
right. So what you need to do now, like how it increasing, you're gonna use the shift, the second function, or the inverse. Different calculator use shift. Some calculator use inverse. Some use second function.
Oh,
So you're gonna press that and press the engineering key, and you will see the number go down. That negative number.
you go down to negative 9.
All right. Go right down until you see the number start zero point something.
Oh, okay.
You see it?
You stop at negative 3 though, you know, past negative 3. That
In a
means,
part, no,
no, my calculator maybe not go further than that. So maybe
no
it
man.
stop to it stop to 0.0000001 to times to the negative 3.
So negative 3. Okay. All right. So it look like it can't pass that.
Can't pass that.
All right. What you're gonna do then? All right. You're gonna put it in the equation. Let it stay back in the 10 to the negative 12 times 200 to the negative
I
3.
would, no, I would do be 12. I would have been 11, come I say at 10 to the negative, so that move one space, so that 10 to the negative, then be 10 to the negative, 10
No
to
man.
the negative.
No. Just put in 10. Just put in 10 exponential negative 12. It will work out by itself.
Okay, negative. All right, yeah.
Mm-hmm.
12, yeah.
Right. And then I put in multiply by 200 exponential negative 3.
Mm-hmm.
Alright, so put that in the whole entire equation now. Remember now
Me
you're
get,
gonna say 1 divided by 2 times pi times the square root of L times C, but you have to convert these first. Convert them, and whatever you
convert,
get, you
convert
use
that. So
it.
convert that now. So that have to divide this. You have to find the square root of this first.
find the square root of this when I multiply this two. Find the square root of them.
Oh, find square root.
Courtney, you following? Courtney? Alright, let me see if I can get a calculator. Courtney? You there? Let me see if I can get an online scientific calculator. The Casio ones are good ones. Alright. Um, it's not a good one. Mm-mm. Mm-mm. So on here with the second function. Alright, so let us try it now. What you're supposed to have now? 10, 10, uh, exponential, negative.
Go no, me get 11,000. Me get 11. No, me get what? No, not 11,000. This me get. Yeah, me have to go. Right.
How much I get? Tell me how much I get.
Get one. Me get what is that? One 2599.93.
What again?
One one one. You hear me?
Yeah.
2599.93.
11225.
99.93.
This is what it's supposed to be getting. It's supposed to be getting in this region. Or let me look at this answer something.
But I reckon put up as a scientific calculator and it make a work it out and see if we get that. I use the value we get here saying.
Okay.
I'm gonna find the square root. I'm gonna find the square. Close that. I'm gonna find this.
Alright. Mm-hmm.
The exponential. See, the exponential. So you have 10. 10.
So this is the exponential right here, sir.
Yeah, 10. That is 10.
Mm-hmm. All
Mm.
right. So we're gonna say
10.
10
Exponential now.
exponential.
Negative
This is
12.
negative
Negative 12
12. I'm gonna press equal.
equal. I
Alright.
get that.
This is what you did get.
Me get that.
Cause what
No,
that
but
mean?
no man,
No.
no man, no,
Eh,
that no,
it's
that
alright.
no.
Hold on. Let me see talk with. One exponential 3.
Equal, not equal that
This
that's
is
what
supposed
that
to
is.
be a thousand. No, this not. It's not record right. One exponential
Uh-huh.
3.
I know my writing up, but me just
But it's your one exponential. I don't like what I want to work.
no man like corner. You have a scientific calculator with you,
No, I'll leave it at school.
but me work out mine.
Mm-hmm.
It's a miracle the 10 exponential to the negative 12.
All right, hold
We get
on. Let,
right
let,
now.
let, let me bring up the PowerPoint. All right. Let me work it out in PowerPoint.
Work out.
Courtney, you
Good.
with us? Courtney, are you with
Yes,
us?
sir. Yes, sir.
Okay. Don't go sleep, you know.
No, no, I'm not.
Okay. All right. So let me just make this up. So FR
If
frequency is
equal
equal to
to
1
1
Oh,
over 2 pi
over 2
oh,
pi
five,
times
pi.
three root.
3.14
Three. Okay, five.
times
Square root
the square
Square root
root
times.
of L
L
and
times
and
C.
RC. So
No,
we use L
let's
first.
try to follow them. Like we don't follow them. Let's try to follow.
L
10
is how much?
L
Mm-hmm.
L L is what?
Ten,
10 10
10, 10 a
10
million Henry.
10
yeah, 10 million.
milli any.
All right. So you're going to then 10 divided by 1,000
You know, we get that. We go get
times how much is now? 12 or 100?
no man 12 200 200 200 200.
200
Mm.
divided by one, two, three,
But them, you know,
4, 5, 6, 7, 8, 9, 10, 11, 12. If you're not using a scientific calculator, this is what you're going to end up have.
So
You're going to
the
have this
first
big number here.
the first step is
So
to the
so
10
um so work out this part first and see what you get. Right?
0.01
That last
0.0
laugh that
0.01.
0.01. All right. So we're gonna bring it down. FR equal 1 over
So how much zero that one there?
two times this. Two times this is what 6.6.28.
Mm,
So how much zero the
Six
filler there, so?
point two eight.
that's
12. So that is so all of this goes 6.28 times the square root. This is how much right here. So 0 point too much.
mm,
0 point too
zero
much.
point zero 0.0.01
0.1 times. So this is
times
so 200 divided by 1, 2, 3, comma 1, 2, 3, and then a comma right here. So that's a million. 1, 2, 3. All right. I thought so you have how much this now?
I come this that's supposed to give you
Mm-hmm.
yeah, negative exponential negative 12.
Mm-hmm. So it is 200.
200 divided by 12 by 12 zero.
Mm-hmm.
So you go have one, yeah, let me just put it on the calculator. So you go have 12, 200 exponential negative
It's
12.
a million, billion,
So you go get
100,
two,
100 billion.
so, so my calculator now give it to you more than something zero, but guess what? No,
How much you're going to get? 0 point something. 0
you
point.
go get 2 times 10 to the to 10 to the to 10 to the negative 10 power.
Going again?
So you go put my you go get
No.
zero. Start me start now. I just at 10 0 10 0, you know.
Mm-hmm.
You go have 10 0 before you go have 10 0 before the two. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then I have two now. Then I have write two.
Oh yeah, for this.
Yeah.
Right. Because that class left that and that class left. That's it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Mm-hmm. Yeah, man. Mm-hmm. All
You
right.
go multiply. You go
So
multiply that.
so multiply these two first and see what you get. Just multiply these two and see what you get.
Multiply that by 0.01. I mean multiply that by 0.01. Me get multiply, you get 2
2.
in bracket.
When I multiply this, how much I get?
You get 2 to the negative 12 power.
All right. Which is pickle. You don't want that. So
Yeah.
divide that to the negative 12 power.
You
Um
square root of that. You have to find the square root of that.
no yeah, all right. Find the square root of it and tell me what you get.
All right, square root of.
I get a small number.
You get 1.414 to the negative 6 power.
All right. You
1
don't
point.
really want it like that. All right.
Eh?
To the negative 6 power. All right. Press the shift engineering until you get to 0. Press the shift engineering key until you get it out to the 0 then. We don't see no more negative on it. You do that?
All right, let me say what I'm going to get.
Me not sure. Me no remember.
All right, what? No, let me tell you what I'm going to get. Negative 6 power. Let me tell you what I'm going to get. All right, I got 1.414. All right.
After I multiply this by this, hold on, let me see if I can use a calculator and do it so way. 0.01 times.
All right, I guess I'm getting myself out. So now I
Hmm?
get 0.0,
How much zero? It's 11 zero.
no, I'm not guess I know my calculator I got still put in now one forecast. If you now me tell them I get 0, me tell them answer me get
Mm-hmm.
0.001414 times 10 to the negative 3 power.
How much I get?
I get
0 point how much?
right is right now zero point
Hold on,
zero
hold on.
zero.
Wait.
So
Alright. Tell me how much I get. I get what? 0 point what?
0.1414.
141 again.
Yeah, times no man, no one, no times. You take off the last one off it. Take off the last one off it. Erase after. I see. Erase a one. Let's see it. I can see it right there. So put put a four behind the one. Put a four behind the one now.
Put a 4 right here, sir.
Right behind the one. Right behind the one. The last one right up there. So put a four. So yeah. Times 10 to the negative 3.
To negative
Yep.
3. Alright. So here we are going to know. You see when you have it like this, just press second function and engineer.
But check, but you see, to me tell you, you see, my
All right.
calculator, my
So you know
fastest.
what I'm gonna do then? You see that zero here? That three here right here, so you're going to have three zero back here. So now one, two, three.
Yeah, so you just move it in front, right? You just move it in front.
Right.
That,
And
yeah,
it
just
will,
move
it
it.
will be this.
Yeah, it's gonna be that.
Right. So
So,
it is 0.0000. This is 50. 1, 2, 3, 4, 5.
yeah.
1, 4, 1, 4. Multiply this now by 6.28.
Put that one between the two four there, so.
Hmm?
That one between the two four.
Right. Multiply this now in your calculator. So just clear up your calculator and type in 6.28 times this and tell me how much you get.
8.8. Me get 8.87 992 to the 6
8.8. Well, again, 8.87 to what?
7.
Mm
8.87.
hmm. Mm
8.87
hmm. Mm
992
hmm. Hold on. 8.87
7
992
99 992
times something to the minus
yeah,
something.
the minus 6.
The minus 6.
Yeah.
Alright.
Just move
So,
6. Just move 5 place in front.
right, 5 place to the front right here. So you
Mm.
got 0, 2, 3, 4, 5, 8, 8, 7. So you can just call it 8, 8.
All right.
Or 8, 8, 8. So we're going to know, you're going to put it over this now. 0, point 0, 0, 0, 0, 8, 8.
But that me get to first time, I'm get the 11 point. I get the number, I give you that answer, I get,
Alright, so 1 divided by this and how much I get now. Check it again.
same answer, I get all of them. I'll do it again still.
Mm-hmm.
I get, I get, what is it now? 11, I get 11, I get 11,360.
Alright, good. Stop it there, so. 11,300.
Hmm. And 363. 63, sorry, 3 for this, not 60.
63.
Point 6.
So if you divide by 1,000, you're gonna get 11.36. 11.36
Yeah.
kilohertz. KHZ. 11.36 kilohertz. Alright, so we're gonna keep that little bit and we're gonna look to see what the simulator say. So the
Yeah,
simulator say
I
106.
calculate even if I do it like 2.0 times 10 to the whatever power. Right, I do
Hmm?
that.
Hmm?
My calculator, it do the multiplication, but it raise it to the power of whatever.
Oh no, alright. When it do like that now, you have to use the shift or the engineering or the second function to bring it back down to where you want it to come down to.
The shift on which one, sir?
Shift and the so it is shift and the engineering key.
Let me see the table, I put up something, I'll put up all of them, so. No, not that, the answer.
112.5.
I'll get 113.
Is it 113 we get our 11 point something?
I look find something.
Mm-hmm.
Oh,
So it's gonna see there. Is this we using? No, we use this and this.
oh, look here. I the wrong to, I the 10 people pick up, man. I 10, I will put the 100 and
Hmm?
the 100. No, the wrong unit to use, you use it at 10. You see the Henry, I for the micro.
Oh,
Yeah, I
so
10 it for the
so so it's so it's 200 milli then
at
and 10
200 milli.
picker. Right.
10 picker.
So do over the calculation then.
Oh,
Do over the calculation.
yeah.
Remember the first thing I do, with us like this, just
Wrong unit to
convert
I
this to
wrong.
Henry, straight
Uh,
Henry. Don't use milli Henry. Just this divide by 1,000
uh-huh.
and write down a number there. This divide by 100 million and you put down a number there.
So this I go give you 0 point, the first one I go give you 0.2 Henry.
All right, put on that somewhere. Put on cause that correct. Put on that somewhere.
Henry.
And then this now, This divide by so 10. Let me see if I can do it as well. 10 divided by 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright, so I get this. I get you see the value I get a while? The value
No man,
here,
we
right
get
right on this. The value here. Where's me have on the calculator?
so this way one, two, much zero. One,
One, 2, 3, 4, 5, 6, 7, 8, 9, 10, and one
yeah,
is
that
11.
when we get to 10. So it's gonna be alright. Let me write down about it there. Wait there.
So
Alright.
write down the value here.
1, 2, 3, 4, 5, 6, 7, 8, 9,
And this
5, 6,
multiply by how much I get? 0.02 for this.
0.02. Yeah. 1, 2, 3, 4, 5, 6,
Multiply
7,
by 0.02, and you get this. Multiply this now by 6.28. Multiply that by 6.28.
me get one, me get one
I get
point,
this.
me get one, me get one, me get one, yeah, me get that. Me
Alright,
get
so
one,
clear off this.
yeah, 8.6.
Oh no, we never find a square root of it, you know.
No, we never find the square root, yeah, we never
Hold on,
find the
hold on,
square
hold
root.
on, hold on. Go back again. What
Yeah.
the two number with the there?
We get two, we get 0.2 times 0.2 times um
Hold on,
10
hold on,
0.
hold on. 0.02,
No man, 0.2, 0.2 times,
0.2
yeah,
times 0
times
point almost 0,
10.
which is this. Right? I'm going to find the square root of this now. Just like how you can find the square root of 4, so I have to use a scientific calculator right here. So if I do this 4 square root, see, let me do that. So I have to put down the number first, then press the square sign. So I'm going to put down the number first, and then I press the square root sign. So this is the square root that I get to the minus 6. So if I put 60 behind this, alright, so I'm gonna use this. I'm gonna use this.
Get 1 point, we get 1 point much?
Hmm?
We get all of it. What do you answer? We get all of it.
Hold on. This 1.4, but it's an exponent to the negative 6. So I'm gonna use it as it is. That's the square root that I find like a while.
Multiply it, you have to multiply that by you have to go multiply that
By
by
by 2 point um this is what
what does six, just put 6.8, 6.28. Just multiply,
six
that's it.
6.28.
Yeah.
All right, times
Six
six
point
point
six,
two eight. So
that's
it's
six
equal to
there.
that. So I'm gonna hold this now. I
What
just
I
said
same
it.
thing you get?
I look like a cent we get.
No man, that's something not right then man.
So
So much
so 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 it is gonna be now 1
no but not
divided by
but I see a man say get all of them
this.
myself.
See it now, you get the right thing.
Yeah.
112.5.
Yeah.
See it right
Mm-hmm.
here, so?
You divide by like 1,000 now.
Yeah, yeah, right.
You
I
divide,
divide by 1,000 now.
mm,
You divide it by 1,000. Get it in the kilo.
yeah.
See it right here, so?
Yeah.
See the point right here?
Yeah.
112.5 kilo.
Yeah.
Alright? So this correct. So the
Mm.
equation correct.
So I
So
just I
so
the wrong
let
thing.
us look at this now and see what we get for the simulator. We get 106 point something. You understand?
I'm
But in a
tolerance.
kilo.
Yeah. It's
Right.
I see it.
So the simulator now give you the exact thing, and those are some of the observation that you have to write down when you're doing your simulation and your observation. That even though the calculation give you that,
Mm.
as and the simulator will give you that. And if you have an
This
actual oscillator now, if you have no oscilloscope, if you have an actual oscilloscope, or
yeah.
if you use the electronic workbench, you're gonna get something different too. And also, if you use Tinkercad, you're gonna get something slightly different as well. But this is not far off. It's just the way you only design the simulator.
If you use the
All right,
same, if you use maybe
right,
if you use the
all right,
capacity,
all right. We're gonna see what we get using the oscilloscope now. If the oscilloscope is different from the frequency counter, so we're gonna check the oscilloscope now, and I'm gonna tell you how they do it with the oscilloscope now. All right, so we're gonna use the oscilloscope. We're gonna turn it up a little bit, and we're gonna use um we're gonna change the color. So I'm gonna change the color and get a little yellow color or something. Alright. I'm gonna turn it on again. I'm gonna run it. Not there, so we're gonna put it in now. Alright.
maybe
So
maybe I have to zoom it.
no man, I'm gonna big it up now. Alright, so alright, so I'm gonna put it in now. So sorry, wrong thing I'm doing. Put it back at the zero line, yes. So this is what I'm supposed to do now. So I'm going to there it is now. Alright. So we're gonna look at the time division. So the time
I'm
division
getting
for it right here, so it's 10 microsecond. But guess what now? We're gonna stop it. We're gonna pause it. I'm gonna do some check it. Hold on, we could go on again. 'Cause I want to get several of them. Alright, let me see if I can slow it down and get a little bit bigger. Alright, and stretch it out a little bit more. Right, and see if I can pause it here. So, alright, good. So I'm gonna use that now. I'm gonna check the frequency now. So I'm gonna check the frequency between two right here, so and right here, so right. So here's what we're gonna do now. We're gonna look at the division now. One, two, three division. So we have one, two, three right here. But look here now. We have 5 microsecond per division. So each division is 5 microsecond. You see it right here, so each division is 5 microsecond. So we have three division. One, two, three. We actually have one, two, three. Even though this look like at the end of the half right here, so and right here,
a
so
three thing,
but
a
one,
three
two,
there.
three. All
I'm
right.
punch as three thing.
So we're gonna do now. You're gonna you listen to me now. You're gonna multiply this three times five, and three five is how much? 15.
Yeah.
15 microsecond. All right. So 15 microsecond. So this microsecond right here now, you're gonna multiply this by 10 to the 6, or about a million. So 15 times a million is how much?
15 times a mil,
Mm-hmm.
15 times a million.
Mm-hmm.
Microsecond.
Yeah, just type in 15 times 1 million.
Me get to find 5 to the negative find 5 to the negative 5.
All right. 1
Find 5
divided by, well,
one
what you get?
1.5 times negative 5.
Hold on. 1.5
Times 10 to
times
the negative
10
5. Negative 5.
to the minus 5. We can move point five five space it behind,
Yeah.
right? So this is one, two,
A, a 4-0
three,
before 0 4. 4-0 before the
four,
one.
five. So the point
4-0
stop
before.
right here. So
So
so we have a point right here. So it is zero point zero
a
zero
4 a 4-0 then I have one
zero
point
yeah
one and
zero
one
one
five.
5. All right. So it is now one. Remember the equation here now. Fr is equal to one over time because a microsecond we are dealing with. Remember the equation there? And use because this equation it will come on the exam again. You understand? So it is one over 0.00 more zero.
Me get 5 6 pints. I be a 6. Me get 5 6 pint 6 6 6 6
How much I
pint
get?
6
If R
6
if R is equal to much?
6 6 6 6 6 pint 6. So you have 5 6,
Six
then you have pint
six
6.
six six point six.
6 again before. Yeah, one and a 6 before the pint 6.
Mm-hmm.
Yeah, 5 6.
So it is 66 million. 666 no 66,000.
$1 million. Uh,
66,000 no, sleep me asleep you know 66,666 66,666 um
millisecond and a
um
second.
Earth. No, it's supposed to be frequency, it's supposed to be Earth.
Oh, Earth, yeah,
that
Earth,
that
Earth.
means that means there's something wrong then.
My wrong is,
We're doing something wrong right there, so hold on.
you see like a scale where you put this, I mean, you should have put in a mega there, so I'm trying to think, so you should have started from here, so. No, go
Hold
back.
on, hold on, let me see if I can get rid of this. Keep this. Discard this. Me not gonna use that. Alright, this right here, so.
Yeah, me think you should have started from road.
This a half, you know.
Yeah, that a half, but
Yeah, this a half, and this is. So this
should
is
be
two
two,
then.
should be two, should be
Two,
two,
two.
should be two.
All right. So
Yeah,
multiply this five by two. You get 10.
yeah,
10 microsecond.
then
All right.
times
So that 10 microsecond now would be this then.
would be one. It would be,
That 10 microsecond
it would be one point
would
zero,
be
point
one
one, it would be
over
over
10 times 10 to the minus 6.
uh,
Right.
but listen now, how you do it?
So
No, that's right.
this now that
That's right.
anyway right here, so you go and get back 6 times now.
Yeah, so that no, no, how you do? Just put 1/0.0. You go put one.
1 over
You go have 4-0 now. One.
um
No man, just put 0,
0
0, 1,
one
0,
0 times 4 0
4,
2
4-0,
3 4
1.
1.
Yeah.
All right. Calculate that answer so much I get. 1 divided by that answer. Tell me how much I get.
I get 100,000.
100,000, which is
I divide, and then I divide that by, I have to divide that, and then divide by,
no man, no man. This divide by this,
I get
cause
100,000,
this is the timing.
100,000.
I get 100,000.
Yeah.
How much we did have?
It have, it have, it have 100, it have what?
This is 106,000.
Yeah.
But you have
I have 100.
100,000.
So all of the answer then are gonna be the right
Yes,
same, you know.
exactly. It close. You understand? And then this is 112.
Mm-hmm. So yeah, same thing, man.
This is 112,000.
Mm-hmm.
So why we get what we get. Guess what we get. We left
I
off some of
roll
the
off,
pints them. I run the
roll
round
off.
off. Exactly. Right. So right away you're familiar with this equation and you're familiar with the other one, which is let me show you so that you can get used to it. frequency. See the equation right here? F is equal to 1 over t.
Uh-huh.
Right. So this is another equation that you use to find frequency. And you can use this equation to find any of the frequency for any of the oscillator them. As long as you know the time, as long as you know the timing for the oscillator, you can find any frequency by saying 1 over the t. And if you want to find the time, you say 1 over the f. You understand?
Yeah, the transpose equation.
Yeah, don't, you just transpose it. Right? See it right here, so? See it? F is equal to 1 over t, or I can say t is equal to 1 over f. Right? And that's where you get those type of equation. Alright? So let us just go back now. So we understand this. So you can read out this because all of this is in the classroom. So we understand the LC oscillator. So we're gonna look at the um, Hartley oscillator. We look at the culprit last week, and we look at the clap. You did have it written down for the clap oscillator.
When you
Alright,
write it, but I don't
because
have
we can look at the clap oscillator. So we can look at it. Because we can find one for the clap, and then we'll go back to the Hartley. Alright. See this one that we were working with last week. Mm-mm. I want something with actual value. You see that C here? You see that C here? This
a
right
three
here, so?
capacitor. That means I have a three,
Right,
a
right.
three capacitor.
Yes. For the three capacitor, but they gotta use C3. Let me show you something in the oscillator. You see this C3 here? They say they make this oscillator smaller than these two oscillator. So they say if it
Capacitor.
is right, no capacitor means sleep, not sleep. These two capacitors is smaller than this one is smaller than these two. So what they say is that you can use this in the equation with the L,
Oh,
or you can use these two with it. You understand? Either use this and it, but they say the best one to use is this.
oh,
So whenever you want to find the frequency, just use this and done.
okay.
You understand? So I try to see if I can find one. See it right here. Usually the value of C3 is much smaller than C1 and C2. As a result of this, C is approximately equal to C3. In other words, the total capacitor for the three of
Got it.
them is equal to
Oh,
C3.
me get what I said. No, because the trees are reciprocal normally than equal to the smallest one.
Yes, exactly. Therefore, the
Oh,
frequency of oscillation is 1 over 2 pi the square root of L time C3.
oh, me just give me understand that because the trees are reciprocal normally when they do a reciprocal is
Yes.
supposed to be equal to the either less or equal to the smallest one.
Exactly. And the so it was smaller, the smaller. All of these going smaller. So they can use this instead. All
I mean,
right.
understand.
uh All
But
right.
it's right. That one.
Um. So and that type of oscillator is a clap oscillator, right? And the clap oscillator now it has a capacitor in series with the inductor, but you still have two capacitor in series,
Okay.
right? And I want to check it out. They're not, these two capacitors are not really in series, right? They are in parallel because you have a common point right here,
Okay.
right? And this common point always go to the grounds, all right? But remember now that when you see an oscillator like this is a clop oscillator. It have the two
Cap,
capacitor right here. It have a common
capacitor.
point, and it have the inductor and the capacitor in series. All right. Let me see if I can find another one. All right. So we're gonna look on the sculpture right here, so and we know that this again right here, so is the clap again, right?
That a clap?
Yeah, it is this a type of clap.
Clap that?
Yeah. Hold on. We go back again. See here, this is the clap. See, single frequency, culprit and clap. One of them is culprit and one is the clap. This is the clap. This is the
Yeah,
culprit.
okay. Okay.
This is
Yeah,
the clap. This
yeah.
is the culprit.
Mm.
See, I have C1, C2, and this is C3. They call it C0, which is with the C3 in series with
Okay.
the inductor. But this is the clap with the two capacitor with the command point, which is really the output, the command point at the output, and then
Mm.
the capacitor right here. This now is the culprit oscillator. We're gonna look at a video with it. Courtney, you're sleeping, man. We not hear you. Courtney.
No, sir, I'm not sleeping there, man.
Once everything's
Alright.
perfectly
Okay.
organized, I'll start working on my thesis.
In this video, we're going to talk about the Colpitts oscillator circuit. So this circuit requires a single NPN transistor to work.
And what's the purpose of the transistor again? As a
Now we're
switch
going
and
to use
switch
the
and
emitter
amplifier.
resistor RE,
That has a switch here, so.
which helps to
Yeah.
stabilize the circuit. And across that resistor, we need a bypass capacitor.
Don't worry about that.
The bypass capacitor increases the voltage gain of the circuit.
Hmm.
And we're going to have another bypass capacitor at the collector
All right. And
of the transistor.
usually the purpose of the bypass capacitors and sometimes they call it a coupling capacitor is to cause a sinusoidal wave to pass through and it block the DC. In other words, they don't want the DC to go into the output and they don't want the DC to go inside of the circuit itself. The DC is to just bias it. Sometimes they put another capacitor right here, so at the front to filter out any DC going inside of the base. They just want to have a pure signal going in, a pure sine wave signal going in, and a pure sine wave signal coming out. So if any DC is coming right here, remember the purpose of a capacitor is to store a charge and block DC, but allow AC to pass through.
So this is the base, this is the collector, and this is the emitter. Next we have RB, the resistance associated with the base, and RC, the resistance associated with the collector. Now instead of using RC, you could use an RFC, or a radio frequency choke, something that has a very high inductance but low internal resistance, which works well for the circuit. But it's not required. You can still make it work without the RFC choke. You could just use the resistor. Now here is the important part of the circuit. We're going to need an inductor at the base, and then between the base of the transistor and the ground, we're going to use a capacitor, and then between the inductor and the ground, we're going to have another capacitor.
Alright, I'm gonna stop it right there. So you see it now? These two capacitors are in parallel. This is the middle of the two capacitor.
You answer something, Mr. Hudson?
Ye- Hold on. Sorry,
You
hold
answer
on.
something?
Oh yes, sorry about that. So remember I was saying that these two capacitors are in parallel.
Mhm.
Remember?
Yeah, yeah.
And then we have a grounds right here, so the negative grounds right
Mm-hmm.
in the middle. So it's just like you have something like this. You have one capacitor here, another capacitor here. I have the grounds right here, and this and these look like they are in. So these look like these two look like they are in series, don't it? But if I
Yeah,
join
but it
inductor
got
right here,
appear to be that, but it got to ground.
it got to ground. So therefore, then they are in parallel.
Yeah.
You understand? They are in
Mm-hmm.
parallel because if I have a circuit like this, and no matter if I put this capacitor up here, so and I put another one, this one, if I put it up here, so and I put this right here, so these two gonna be in parallel.
Yeah.
You see it now? Because if I
Mm-hmm.
draw this and put this to a transistor, where that one going?
Mm-hmm.
These two gonna be in parallel. You understand now? So whenever you see the culprit oscillator, and you see this point right here, so between the two capacitor, these two right here, so between the two capacitor, they are at a common point or a common ground.
Okay.
Right? So let me just go back to this now. So see it here right here, so this is a common ground right here, so alright, let me just show you another one. It's right here. It's right here, so the common ground between the two of them. Let me see if I
Okay.
can get another one. Um, so one right here, so you see it again with the common ground.
Yeah.
Even for the clap, it's the same thing, right? And for the culprit, see it here, so again, and where's the ground? That means that even though they straight out and look like they are in series, they are really in
In between
parallel.
two capacitors. In between the two capacitors.
Yes, they are really in parallel. They are not in series. If the ground wasn't there now, you know that they would be in series, right? Here's it again. See it? So even though it's a common ground, sometimes they use it as an output. Let me see if I can find another one for it. Here it is again right here, so. Here it is again right here, so acting as an output. You see it? We can look at this with a transistor. No, no. Alright, which one is this? Is this a clap or a culprit?
Clap.
It's a clap. Oh, you know it's a clap.
Because it's something the inductor and capacitor in series
In series, right? And these two are in parallel.
that are parallel.
That, yeah, and they look like they're in series, but they're not in series. They're really in parallel, right? And here it is. Here's it again. See them here again with the ground. See the ground? This ground can't do any point at all right here, so you know, right? So this one, if you can try this one on the simulator, if you can try this one on the simulator, I'll see it works. The one here.
Copy it and put it in the cylinder and so go.
Um, well, it can't copy straight. You have to draw it.
Yeah, copy. No,
It
how many use?
can't
How
copy.
many I use on software there? I use as, but I know it's.
Mm.
I use. You see, in something yesterday.
Deeds,
Yesterday.
deeds. You can do it in a deeds,
Yeah.
but you can't do it in a this. And this would be the output, and this would go to the oscilloscope.
Okay.
You understand?
Mm.
So you'd have to give this and well, let me see if I can find one of this somewhere down here. So all right, see one of them down here. See it, and it give you everything right here. So we can probably try this one, right? So we're gonna have to count how many resistors there first, and then we make the tank circuit. We can make a tank circuit first. Jar the resistor, no, jar the transistor. Put on the two biasing resistors. Put on an inductor right here, and then use a 2N2222 transistor with a bypassing capacitor right here. So I'm gonna try to see how much frequency we get out of this. What's the frequency they said they're supposed to get out of the one here?
10%.
Mm-mm-mm. Um, no, the frequency. How they calculate the frequency for this? And what they do the frequency for that? Because they don't have any other capacitor, they're gonna use these two capacitors. Right? They're not gonna use this one. They're not gonna use any other capacitor apart from this. I could just fast forward this right here, so I see something. All right. So so this is where they're gonna put the frequency. And I'm gonna show it. But you could use it right here, so. And we know that this is C1 and C2. So see if we can work out this one and this one. Don't use the 4 volts in it. Use these two. This is nanofarad, and this is 5.8 microhenry. Alright, use the one with the millihenry and the microfarad. Start it to work out faster. And see if we get 4.77 kilohertz.
Really, let's say 0.04,
Mm-hmm.
0.4
0.44 microfarad,
microfarad.
right? And
And
9.56 microfarad. But remember now that because these now are in series now, and because they are in series, no, they're in parallel. If they're in parallel, work them out in parallel, which is this multiplied by this divided by this plus this. Product over sum. Oh no, sorry, no. If they're in parallel, they're supposed to add. If they're in parallel, so add them up and see what you get. Just add them up straight like they are first, and then you convert it because they have the same. They have the same unit. So add up 0.44 plus 9.56 and see what you get.
we get 10 microfarad.
You get 10 microfarad. Alright, good.
Yeah.
Convert the microfarad now to farad. And you don't know how to convert it already. The microfarad to farad. What you do, you multiply or you divide.
A micro this a mic million micro that to 1,600 to
Hmm?
a million.
Alright. Yes, to a million. So we do, because it's 10, you're gonna multiply it or you divide it.
Divide.
You divide it. Divide it and put on a number there.
We get me have to get this. We get 0.00001.
Alright, put on that. Put on that number there. Alright, 3.71 now. You're gonna use this 3.71, which is this right here, so 3.71, but it's milli. So you know that is 3.71 divided by 1,000.
Zero 0.00371.
One. Alright. So you're gonna multiply those two now as they are. How much you get?
We get we get 3.71 times 10 to the negative 3.
Find the square root of that.
Yeah. Yeah, me come. Give me a second there. All
Mm.
right. 3.71 10 to the negative 8 by negative 3. Right, square root of that now. 3.71 so 10 negative 8. We get 1.92
All right, multiply that by 6.28.
multiplied by 6.28. We get 1.2096 to the negative to the whenever to the negative 3 power.
All right. See if you can do inverse engineer and see if it's going down to 0.00 something without negative.
Come on, can I get that? Let me go get 0.00120 0.012.
All right, put on that number there.
Mhm.
Put it on a piece of paper or something.
Yeah.
All right. Now you're gonna say, oh, one now divide by the number we put on a piece of paper. Then go on.
We get 8.33
Get
point
point
3.
three. Get point three three. We're supposed to get point three three.
Let me get some go.
We're supposed to get point three three. Do these in series and answer something like a bit. Do them in series. Just convert this back to what it was. Convert this back to what it was. Especially if you don't write them down, we can keep the number them. Do it in series. In other words, you're gonna say this.
Just multiply.
You multiply and product of a sum. Just multiply these two and divide by the sum of these two. How much I get?
I come, uh, we get we get 0.42, you know.
0.42 are good. 0.42 multiplied by this now but you have to put convert this to Henry.
Yeah.
3.71 divided by 1,000. So put on the number we get for the microfarad them. Put on that first 0. Point whatever, and then you convert the Henry, the millenary to Henry.
We get 0.0155.
0.0155.
55. But we never find this. Yeah.
Hmm?
So so we never find the square root of this now.
Yeah. Hold on. When I get this, there's a number where you get while we name. Why you get 3 point something or 2 point something?
Yeah, multiply by the answer a while ago. So if we find square root of this.
So you multiply by the answer. This one, you convert this to.
Yeah.
All right. So find the square root of it, not of the combination I know.
Get 0.0
Multiply that by
point 38.
is 6.28.
We get 0.247.
All right. You get it now. You just get it a while. So you're gonna say now. Put down that number there. Put down that number there,
Divide by 1.
and then you say one divided by it now.
We get 4.04. Right, man.
4.04.
Yeah,
Because me say some 4.7 something, you drop off something, you know.
no
You
me
said,
drop off some
you can you say, you say 0.47 something, look while. Where do the 7 them? You fling with the
no
7
no
them?
come on, so no 0.4 0.247, divided by one,
Hold on, 0.247, 247 to get?
0.0, when you get when you get zero, how much now?
At 0.4 something you get, man.
When you get 0.247.
0.247.
Mm-hmm.
Mm-hmm.
I'm gonna divide it with
One divided by that, how much I get?
4.04.
4.04.
Yeah.
You're supposed to get this.
A 4.04 me get.
Mm, we're supposed to get this. Boy, get the 4 still.
Yeah, let me have
Uh,
on
mm-hmm.
the fact. Yeah, yeah. 4 point. Yeah, the four.
All right. Look at where they get down here. So same thing on them do. And look at them do. And so them get there.
Mm. Let me do that. Let me do that. Wait there.
And this is they get, you get 0.42 something.
Mm. 0.04. Mm-hmm. We get that. Get but
Mm-hmm.
0.42. But
Mm-hmm.
you have to multiply that by
Mm-hmm.
the Henry now.
Mm-hmm. See it
Multiply
there?
that you have to multiply that by
See there with this and
mm-hmm.
this. So this up with the capacitor, I
That have to,
guess.
mm.
Uh,
No, that have to the
no. It's up for the inductor. It's up for the inductor, right? Yes, sir.
mm-hmm.
This and it's up for the capacitor. Mm-hmm.
Oh, this is what go on. You're right, man. You see,
Mm-hmm.
when we do the calculator, me never put me never put the 10 to the negative 6. Never
Oh.
right.
Mm. If you divide by 1,000,
No, you
you
see,
see,
the brackets, me not this month.
see the one here. If you
So me
divide
get,
this by 1,000 and this by a million,
so when me get it
the,
wrong. Me just multiply by
mhm.
0.42. Me never put it to times to the negative 6.
Or are you never divide by a million? Can divide by a million,
No, man, so me never divide it by a million.
You should have divide by a million.
That's
So
right.
so do it now. Divide the 3.71 by 1,000 and divide the 0.4206 by a million,
Very good.
and then you find the square root of it.
3.1. So me get four thousand three 32. 4,032.
You still
But I
left
have to
off
go
something. You still
but you
left
have to go
off
divide.
something.
No
You
man,
still,
but you have to go divide that by 1,000 now. Or divide
what
by
that? No, it's
you get
supposed to get.
4,000.
It's supposed to get 4,777.
Maybe I order round. You don't
Can
know.
you can keep on dropping off things.
No, me not drop off nothing. Me just
You don't have nothing. You know?
I,
Oh,
yes,
no, this is how we get 4,029.
I
And
me
that's
get
again.
4,032. Me get 4,032.
Oh, let me say it can go on.
Divide. I divide that by 1,000.
Uh-huh.
I divide by 1,000. I'm supposed to get.
Mm-hmm. 4 kilohertz.
Mm. So me get. Yeah, so you get. Them get 29. Me get 32 instead.
Mm-hmm.
You understand me? I say.
Uh-huh.
Let me divide that by 1,000 now. I still get
The
the
four,
four point.
you get 4 point something.
Yeah.
4 point too much I get.
Me divide. I'm gonna get 4.0. Me divide that by 1,000.
Mm-hmm.
Me get 4.03.
Right. As long as I get the four, you're good.
Yeah.
Because see my 4.77 up and them are four long so. And it's the same calculation. Right? So we understand that from the culprit and the and the and the clap. So that's the culprit and the clap. So we're gonna look at the Hartley oscillator now. With the Hartley oscillator now they use two coil and a capacitor.
Team City will help you to get started with
Same
continuous
place where they would have
integration for free. Every big thing.
the same place where they did have the. Hold on, let me go back a little bit. So what one you do you see try the one on a simulator when you have time and see the frequency we get for this one. Um, let me just go back a little bit. I mean I'll get to me more right there so sorry. One get me can't me not get it. Hold on. Alright, so we're gonna look at the Hartley and we did look at the Armstrong already no? No we never look at the Armstrong. Alright, so this is the Hartley now. So the Hartley has two resistors, no, two inductor split it's in series. The Hartley oscillator design uses two inductive coils in series with a parallel capacitor. So these are in series. When it is out, they say it is in series. When it is when it go to ground, they treat it as parallel. So we can treat this as series. So even the one for the capacitors, we record the coil treat it as series with the product of a sum rule.
Hmm?
Right? No, for the culprit that you look while, treat it as a series with the product of a sum rule for the
Uh,
capacitors. But with the inductor, you know, say you got to add them as an inductor. Right? So we can see if we see they're working out. Alright. The two of them right here. So we can see if we see anything down here, so. Alright, here's an example coming up. And it's supposed to get 503 kilohertz. Um, so there's the same thing now. 1 million 100 picofarad, and they have it like this, 6.28, when they convert these, they get this to this to this. So what we want to do, we wanted to try it, or wanted to try it on the on the oscillator. So if you get something like this now, you just put this in on the oscillator, right? But you want to draw the circuit like this, and this
Okay.
would be the oscillator right here. Because if we can get one actual one with the actual transistor on it. Because if we can find one like that. For the Hartley. Alright, let's see if this one hold.
In this video, we're going to talk.
This is Hartley with the two coil right here. So
Now
we're
let's talk
gonna check
about the
these two
output
coil.
of this
So we're gonna go a
circuit.
little bit faster
L2
because you understand
is
what's
off.
going on now.
So first,
Alright, so this is the frequency thing for it now.
so what I'm going to do now is I'm going to multiply both sides by 4 pi squared times LT.
Same
So
thing
you
they're
get
doing.
F squared
Same thing they're doing.
times 4 pi squared L.
You can speed it up.
So go ahead.
So this is C3. This is C3 over here, so right. And so right here. So this is C3. So this is C3 is equal to no, this is C3 that they reckon out. What is the frequency I want them work out?
That's for the formula and then record the C3.
Right, exactly. So once you have this, you know you have LT. I know it's LT. You just add up these two, and C and C3 was how much? What's the value for C3? Did you get
C3 they want to find.
a value for C3?
Right.
Oh,
That,
C3 they want
right,
to
they want
find.
to find. Yeah, that's why they
Okay.
C3 they want to find.
No, me don't want to go to the one with it. Me don't want to do the one other way. Yeah. Let me still the one here with the Hartley.
Yeah. Yeah, man, yeah, me there.
With the Hartley. I say we can get a different one with the Hartley. Where they actually have a circuit on it. Alright, two inductor. Right, Hartley. This is a clap. Hartley. Alright. Alright. Let me see if they have any value for that one here. And they give an example right here, the other one here. With the Hartley seat here. With the two inductor and this example two. And when I record that, they're supposed to get 4.799. So this is an up amp right here. We don't know this resistor and this resistor. Only the tank circuit to know the value. So we try to find one with some values and you put them in the and you put it on the simulator and try it. the one that they use on a solar coil is the up amp they use. What about the one here? Mr. The one you have to have anything for this. No, they're not giving no value for those. Mm-mm. Alright, so next class we're gonna look to see. I'm gonna bring up. I'm gonna put some in the classroom that you can practice on, and for the labs as well. Right. So now that you understand how to find the frequency of the Hartley and the clap and the culprit, then we're gonna look at how you go about understanding the oscilloscope. So we're gonna look at it first now. We're gonna look at this one and this one. I'll call it a day. Which one bigger? This is 5 minutes and this is 17 minutes. How much time we have left? We're supposed to finish 9 o'clock, so we must get done this and dusting in time then. Don't it?
Yeah.
Alright, okay, so we can run it fast.
Hello everyone, this is Ali Reza from diagnosticsolutions.com. In this video I'm going to explain how to use oscilloscope for simulating and measuring AC circuits in multisim. The basic circuit that I'm using here is
I'm gonna speed it up a little
is
bit.
an RC that we are using. The negative inputs should be connected to the ground, as you can see.
So
here, and I'm connecting it
they're
here,
using the two
to
channel.
the
They're using
ground
channel
through
one and
both channels.
channel A and channel B.
So then we
So they
will
use
be
channel
able
A for the
to see
input
the
and channel
waveforms.
B for the
If we
output.
run the simulation and double click on the oscilloscope, then the oscilloscope screen will pop up.
And this
we'll
this
be
is
able to
also this is
see the
also an
waveform.
RC
But there are a
oscillator they're
couple
working
of
with.
things
They're
to
working with an
explain
RC
on the
oscillator right here.
oscilloscope screen. DC component of the signal here, so I put the channel B to 0, so no waveform will be displayed. And usually when we want to display a
Let's speed
waveform
it up a
using
little bit.
see a couple of cycles, this one is a good one for measurement. We can add a couple here, so you can move it on the top. There are be 20 is the other
Right.
waveform, right?
See it here now then do the two waveform and they check this
So if
frequency.
you have two waveforms like the output waveform, we can use the other channel too. So instead of connected into 0, I connect it to the DC, and as you can see here, so the waveform will be displayed. The second waveform is the waveform across the capacitor. And so what we can do, if we want to move cursors on the second waveform, just double click on that one, so it will go on the second waveform. Okay, again, you can measure the amplitude of that one. We can measure the peak value, or we can measure the peak to peak value. It's possible to do that. For example, here from top to bottom one, we are 2.16 frequency, and is for the waveform that we have here. So we are actually seeing the channel A, which is the larger signal, right? So we can measure from difference is to oscilloscope in order to measure. We are measuring the peak from here, and also, for example, say we have a cycle which is 180 degrees, and so we divide 220 divided by 1000. By scale this one to the value.
I'm trying to find out how they do the frequency.
The other.
So that I can
This is
get a
an
better
RC
idea.
circuit. Measure the frequencies, the same thing in a linear circuit. You can measure the 1.4. It will give you the measure from the very top. So this is the one that we are using. So this is the only one that we are. You can see here on the left bottom side on the oscilloscope, and there are also which is a negative, almost 28 volts, and the difference is displayed here. Value will be value, right? So the peak 2, which is 1 for the frequency 500 microseconds. So
Alright, we can look at this.
and the difference, so we can just measure how many divisions on the horizontal we have.
Alright, here it is right here. So
for the
they're gonna do
distance
it right here
between
for now.
these two cursors, which is I think
Let's
it's
go
a
back a little
region
bit.
on the horizontal axis, has horizontal axis, or you can measure from to zero crossings, right? So for the two peaks that we have here, and as I'm moving the cursors, we need to consider the time, which is the horizontal axis, and every division on the horizontal axis has 500 microseconds. So and the difference, so we can just measure how many divisions on the horizontal we have for the distance between these two cursors, which is, I think it's about 2, as you can see here. So it will be like two
division,
times.
what you talking about, these division, the squares them. So,
Me understand.
this is quarter, this is quarter.
Okay, what is quarter, one is quarter.
Uh,
So make this
that's the
give
one
you
right
one.
here. So, with this, cause they include this too, you know.
So that a three quarter, this and that a quarter. So they
Mm-hmm.
just give 1. Three quarter and quarter give 1, so and then you have a full square that give you 2.
Two, so you just call it two and done. And then then they multiply it by the
Times
time division.
500 microsecond,
The
which is
500 also
about a
500.
thousand microsecond or 1 millisecond.
Mm-hmm.
So the period of the signal, which is the time difference between the two peaks, will be 1 millisecond, and the frequency will be 1 hour. That value, which will be 1 hour 1 millisecond, which is a 1 kilohertz.
See? So 1/1 millisecond, and all they get a millisecond, because this right here, so it's 500 millisecond, don't it? And when they multiply by the divisions them, the two, they not get they not get the
Oh, okay.
1,000 millisecond.
1,000,
As
1,000 minutes.
voltage.
Uh-huh. And then the one divided by 1 millisecond give you the 1 kilohertz.
Okay, so
If I put my
another
side,
thing
but
that we need
Eh?
to do
it's kind of
measurement.
blurry. The chip kind of blurrish. I mean, I
Yeah,
see
yeah,
the
yeah,
number.
yeah, it look blurrish. All right.
I'm looking at it.
But to get the gist though, so we're
Yes,
gonna show you one different one.
I'm
We'll
you're
show you.
right. You know, many things are my internet have problem, but it's good.
No man, I
Here
look like on my own.
is
I get trouble.
the other
You can always watch it because they're like classrooms. We're gonna look at the other one.
Okay guys, it's me Imad from Nelson Darwin Parktech for it multi signal. So now we will go for our signals. Multisim has offered us a very important tool that is called as the frequency counter. So you can drag it out, and
So you
now
can use
we
the
will
frequency
go for
counter
our
as well as the
signals.
oscilloscope. You understand?
Okay, now we have our AC power signal. So we can take our AC signal and we will just connect our positive end of our AC signal with the frequency mirror or frequency counter. And also you need to attach the lower end of the AC supply with the ground. Okay, now like it. Okay, so okay, now we will run it. We will see that it gives us the 60 hertz, which is purely okay and right. Okay, so saying that there isn't any. Okay, DC current impulse width sources. Okay,
So I'm seeing if I can
we
go
can see
faster with it.
there are. Now can we decrease it 26 to
So so
27.511?
I'm showing you how to use the frequency counter
Okay,
right here.
isn't any
But I'm not
sort
gonna
of
show you to use the oscilloscope.
message signal in it, message
But
frequency. So it
you
is
can look it
pure
up on at another video
500
to
hertz.
show to see
So hopefully
how
you
they use
got a
how
bit
to
of
use or they measure frequency using the oscilloscope in multisim. So I think we'll stop it right here
Yeah.
at 28.
Come
Mm-hmm.
on, you good. With the whole cover all it.
Mm-hmm.
Cover a lot.
Right.
Nothing wrong with that.
And I know that you get to understand the different type of oscillator you know. What are the different type of oscillator we have again now?
You have culprit,
Mm-hmm.
Armstrong, culprit Armstrong.
Mm-hmm.
Um,
Right.
and
And make you remind yourself how the Armstrong look. And remember now, the Armstrong is the only one that have the inductor and the capacitor. See it right here, sir? And it have the active device, which is the transistor. See it right here, sir, again? This is the Armstrong again. Capacitor and inductor. See it here again? See it? So almost everywhere you look, you see the Armstrong oscillator. You see it all over the place there. And remember now, the Armstrong is the only one with the inductor and the capacitor. And let me see if I can show you one of them. I'm just supposed to show you one of them again now with the no another one here. Is it though? Or the transmitter is the one with the transmitter. Hold on, let's see if I can find that one there. Alright. RF. Alright, look at this one right here. So, alright, so this one is a RF oscillator circuit. Right, and what type of oscillator does it use? Is it a clap? Is it a pulpit?
Man,
Is it Armstrong? Is it a Hartley?
What I say, Armstrong.
Armstrong, right? And they use this one to make an FM transmitter. So this is a FM transmitter with a signal in. Can I put the mic inside here so I talk. All right. Let me see if I see another one. Um, this one would be which one?
That's
Two,
the one that the
two inductor and a capacitor.
doctor this doctor early.
Hartley. All right. All right. The frequency oscillator FM transmitter. All right. And that's the FM transmitter circuit diagram. FM circuit diagram. FM transmitter. Alright. So one right here they use two transistors right here, sir, with the antenna going out. But which one is they use right here, sir? So the oscillator right here. This again is our
That Armstrong.
Armstrong. That's the mic right here. Right, this another one again, a simple FM transmitter. Here's another one with a microphone transistor. Right? So you can try this one and you can actually put a mic on it and see if it transmit. And it use a 9 volt battery. So how do you feel now about making transmitter now and cordless mic? You feel up to the challenge now with the lab them now?
Yeah, you can design it still. Can I go have a blueprint. So just get the material
Exactly.
and design.
Exactly. You understand? And what I want you to know is try it first on the simulator and see
Okay.
it operate. And you can see the frequency. Because right away you can get the frequency out of these two.
You
You
can
can
copy a
calculate.
little,
You can,
can copy a little, put in a classroom.
yeah man,
Some
have,
kind of
have, have, have a whole lot of them. I want
Okay.
all of them, but I don't want to give anyone any two chances. I want to give her the one chances I want them.
Okay.
All right, and that's why you and Courtney gonna do for your projects and your lab them and the major project them. All right, so the major project is one of these is to
Oh,
make a
that I
call.
need.
No man. For this semester for this course that you're doing now.
Oh, me think. Oh, me know. Say I have a course in a major project. I know that. Oh, just remember
Mm-mm.
say.
I know that. And let me just go back to to the course outline. I'll show you. Um, go to it fast. I'll show you. Just remind you again what you're supposed to do for the major project. I should I go right here, so. Alright, this is the telecommunication one. This one electronic device, electronic circuit and device 2. Catch it yet? Not catch
Just
it
see
yet.
it.
Alright, this is still not here still.
Oh,
Still not here. As a far up there. ABC. The next one is supposed to be your one. Alright, another calculation. Alright, calculus 2. ABCD. We don't have nothing for D. We don't have nothing for E. So we think it account now. So the capital major project. That's C. We took one so. Capital major project. Go back up you know. Cloud computing. Computer system security. Alright, so this is it now. So we're going to go down to the rubric. And you see the rubric again we're supposed to do. And what you realize? You realize every pass you pass a oscillator. The Wayne bridge and the RC feedback and the clap oscillator and the culprit and the Hartley and the Armstrong crystal control oscillator. And almost everywhere you go from unit 1, start off with oscillator. Oscillation again using the 555 timer. Listen to the communication circuit. These are the AM and FM receivers and transmitter them. So the P oscillator, voltage regulator, field programmable analog array. Alright, so see it here now. So practical test, 30%. Right? So the practical test, you take it from unit 1 and unit 4. So we're gonna look at unit 1 and unit 4 again. I'm going to see what you're supposed to do. I'm gonna see what you're supposed to do for the major project. I'm gonna see what going on. Unit 1 and unit 4.
where the major fork come from?
Hold on. The practical test. So the first
Come
practical
from
test
this
are
one.
come from this oscillator.
Yeah.
You understand? Mm-hmm. And unit 4. See it? The second practical test, Unit
What
4,
is
a
regular?
voltage regulator. Alright. Go back down again now. And then you have a theory test, which is 10 questions. So it's 10 multiple choice you're going to get for this.
Unit 1 to Unit 3.
Alright. And it is from Unit 1 to Unit 3. Right?
So
And,
the,
it's in the Google Classroom, so you can get it. Unit 1 to Unit 3. Right? And Unit 1 to Unit 3. Excluding the regulator. So this is Unit 1, so Unit 1 is strictly everything oscillator. Unit 2, 555 timer oscillator again. Electronic communication circuit, FM and AM transmitter, receiver and transmitter. And if we come back down to this now, you have a group project. You understand?
yeah.
So the group project that I wanted to do is really the transmitter. Right?
Okay.
So you're gonna make some little small lapel mics, some cordless
Yeah.
mics
Yeah.
that look like it can sell. So it have to look good. You understand? All right, and that's a group project. Young Courtney can work on that, and then you have the final exam. So I'm gonna send the information in the classroom. I don't send anything yet, but I'm gonna send them shortly in the classroom so that you can start to do your thing. Because I'm sending anything is only notes I send, lecture notes. You can go and read this.
That big 5 minutes coming up to do something right now.
No, I'm going now.
Okay.
I finish up now. All right, so that is it. I'm gonna stop record.